Hello students, welcome to the course Network Theory. In the previous video, we tried to understand the concept of node analysis with an example network. So how you write the node equations. Okay. With this knowledge, we have written the node equations along with how to represent them in matrix form and how to apply Cramer's rule for that, and even how we can write the general equations for a node. Okay, so with this knowledge we try to solve two problems in this video, uh, definitely with linearly independent current sources and voltage sources present along with resistor. Okay, that means a DC network problems we'll see. So first problem, so just note down, using node analysis, find the voltage V1 and V2. These are nothing but the node voltages of the circuit shown in figure. Okay, so you have a circuit here, 12 amp current source, 4 ohm resistance, 5 ohm resistance, 10 ohm, 20 volt, 5 ohm, 15 volt, 5 ohm, 10 volt. Okay, so just note down this figure. So now we need to find out this node voltages V1 and V2. Okay, so along with these two nodes, there is one more node is also present here in the lower side, that is node 3, that is not shown normally because it is at ground potential. Okay, and it is the reference node. Okay, so that is not taken, so only two we have to calculate here. So to before we do the calculation, so just some changes we have to do. Whatever we have done, some concept we have learned, source shifting or elementary source transformation, so that we try to do here, because normally when we apply node analysis straight away we are applying KCL here. So if we have the current source present over there, then it will be better. Okay, so otherwise you may confuse here, because every time you need to uh, do the conversion here. Okay, so why? Because see here, so there is a 12 ohm source in series with resistance. This is a trivial element, right? So any element in series with a current source is a current source itself, right? We have learned that. So this resistance is just a additional one, so you can remove that in simplification. If you see here, so normally between the nodes we have the branch currents, right? So every time when you calculate the branch currents, voltage divided by resistance you have to do. Instead, if you do the source transformation here, current source in parallel with resistance, so it is easy for every calculation, right? So we can have 20 by 5, 4 amp current source in series parallel with a 5 ohm resistance. If we make, we can easily do. Similar way here also you can see 5 ohm in series with 15 volt. You can make it current source. Similarly this also, so that we can reduce the network into single network. Okay, so that elementary transformation we will do it first. Okay, so it will not change your values of the V1 and V2. Okay, because simplification values will be reflected in the simplified network. Okay, so that will do. So first thing, this will remove 4 ohm which is in series with this, and these three voltage source in series with resistance will convert into current source in parallel and will simplify. Okay, using the source transformation techniques. Okay, so you write down one more time this network in the solution. So that's what I explained. 12 amp current source in series with 4 ohm resistor. So this resistor can be neglected. Okay, so it does not have any effect. Okay, so next voltage source is converted into current source in parallel with resistance here. So it was 20 by 5 is 4 amps, and it was plus minus was there. Accordingly, you need to give the current direction. Okay, so similarly here voltage source were there, 15 by 5 3 amps, and here 10 by 5 2 amps. So the notations, terminal polarities were different. That's why one current you have upward and one current you have downwards. Okay, so next simplification what you can do, you can combine this network, right? So 3 amp current source and 2 amp current source, you can subtract this and you can make it as a 1 amp current source, and 5 ohm and 5 ohm are in parallel, right? So this you can make a single equivalent resistance by parallel resistance formula. So that next you have the simple network. Easily you can write the node equations and use the calculator and solve the answers. Okay, hope you have understood what I told by this. Okay, so we'll carry out this simplification. So this is what 12 amp, this is will not change as it is, 10 ohm as it is. So here also no changes here. So the 3 amp is upward, 2 amp is downward. So whichever is this side we have taken, that's why 3 minus 2 it is 1 amp. And the value of resistance, so both are 5 ohm resistance. So 1 by 5 plus 1 by 5 is 2 by 5. So reciprocal is 5 by 2, which is the 2.5. So that's why here 2.5 ohm is shown. Okay. So now this is the simplified network from the given network. Now you have the two node voltages V1 and V2. So now you have to apply the KCL to write the node equations. Okay, so you can directly write the general equation. So now node 1, what are the resistances connected? 5 ohm and 10 ohm. So you can write straight away 1 by 5 plus 1 by 10 into V1 minus, so with respect to V1 and V2, 5 ohm is there. So minus 1 by 5 V2. Okay, understanding? So yesterday's video, if you have not watched, so just be watch it and then come. Okay, so 1 by 5 V2 equal to, now current we need to write it here. So 12 amp is entering the node and 4 amp is also entering the node. So 12 plus 4, 16 amp current is coming to this node. Okay, so 16 is equal. Then similarly second equation, so how you write? With respect to V1 you have 5, so minus 1 by 5 V1, then self. Okay, so you have 5 and 2.5, so it is 1 by 5 plus 1 by 2.5 into V2 equal to, now current is 1 amp is entering the node and 4 amp is leaving the node. Okay, so entering the node will take plus always, so 1 minus 4. Okay, so if you take reverse also, accordingly it will change in first equation also. So having these two equation, so now use the calculator we have done in mesh analysis for 3 unknowns, right? Now you have to do for 2 unknowns. Okay, so you'll ask only 3 values, a1 b1 c1 and a2 b2 c2, you'll get the answer. Okay, so just we'll see the equation in the next picture. So just write down this network and verify it in the next equations. Okay, so applying KCL. Okay, so since I have not applied straight away general equation, I have shown you here. Okay, so this is the general equation itself. So self 1 by 10 plus 1 by 5 v1 minus 1 by 5 v2 equal to 12 plus 4. Two currents are entering here. So when you take the LCM of this and you write here, so it is 3 by 10 v1 minus 1 by 5 v2 equal to 16 here. You can keep this in decimal. So 3 by 10 is 0.3, right? So that you can enter in calculator easily. So 3 by 10 you have calculated 0.3 v1, 1 by 5 is 0.2 v2 and 16. Okay, so you got the calculator first equation. So this is the a1 0.3, b1 minus 2, c1 16. You have to consider two unknowns. Okay, in equation mode, two unknowns, because v1 and v2 are the unknowns here. Okay, so then it will ask three values, a1 b1 c1. Similarly we see the second equation. So you have the network with you, so just whatever I told, just we'll simplify network. So minus 1 by 5 v1, which is the mutual one, minus self you have 1 by 5 plus 1 by 2.5 v2 equal to 1 amp entering the node plus minus 4 leaving the node. Okay, so 1 minus 4. So now again if you simplify 1 by 5 means minus 0.2 v1. Then if you take the even you can use the direct calculator here, 1 by 5 plus 1 by 2.5. So you will get 3 by 5. Okay, so 3 by 5 you will get 3 by 5 means 0.6. You will get 0.6 v2. 1 minus 4 means minus 3. So you got the second equation now. So now enter this in the calculator. Okay, as a2 as minus 0.2, then b2 as plus 0.6 and c2 as minus 3. Okay, and just click equal, so you'll get the two values of the voltages. Very simple, because it is a DC network, you can use the calculator. So my values are 64.3 volt and 16.43 volt. So just you check your answers, is it correct or not? I am confident this time because I have done correctly. In case any mistakes is there, you can inform me. Okay, you can tell me the things. Okay, hope you have understood. The difference is how you write the equation here. And instead of writing the same network, earlier we used to have three mesh equations and three equations, three unknowns. You used to have three currents, and from current you need to find the voltages. Okay, so now in this, so we have taken three nodes, one node as reference node at the ground potential. So we are writing only two equations for two nodes, and solution is little simpler now. So two unknowns, so you get the two values. So from this also you can find the mesh currents or branch currents now. So that example I will show you tomorrow. So today's is just to show you how to write the node equations and calculate the node voltages. Okay, so similar way I will show you now another example or problem. So where instead of resistance values, conductance values is given. Okay, so what is meant by conductance? We'll see that in the picture itself. So note down this problem, find the three node voltages VA, VB, VC for the circuit shown in figure. Okay, so when we are writing the equation, okay, node equation, we will be writing normally 1 by R, right? So 1 by R with respect to node voltages, it may be V1, V2, V3. So now instead of 1 by R, so we have given conductance, that is G into V1 you can write. Okay, so resistance will be measured in ohm, whereas conductance is measured reciprocal mho or Siemens. Okay, so here see in this network the values are given in mho, right? 1 mho, 1 mho, 1 mho everywhere, right? That means what? This is an conductance here. Okay, so that means you should not take here reciprocal when you are taking the node equation. Should not consider it as reciprocal, but you should consider straight away as G into V1, G into V2. Okay, with respect to that you have to do. So this is another problem, so that's why I taken this example. Okay, so you may not tell I have not done such type of problems. So here there is no simplification here, so straight away you have four nodes are there. So three nodes are mentioned here. Okay, A, and this is the one junction B, and this is the junction, and many of the branches are connected to this lower branch. This is the fourth branch. Okay, it is not named there, it is a D you consider, and this is the reference node, and which is at ground potential, so that's why VD is 0. Okay, so since you will confuse, so I will be not writing any this one. Okay, so the KCL equation and simplifying straight away general equations I am writing. Okay, so now what you have to do with this example, just three equations you have to write for node voltages VA, VB, VC. Use the calculator now. Equation, three unknowns. Earlier we have seen two unknowns, no, now again three unknowns. Three A, B, C, D parameters of each equation you enter, you will get the VA, VB, VC. Simple one. Okay, only thing confusion here is they have given in mho. Okay, that should be careful. So now with respect to A, so what are self? One is here, one is here, one is here. That means you should not take one by one now, it is straight away one. Even you could make mistake one by one also, it will give one answer only. Okay, like that they have given. In case if it is 2 3, 1 by 2, 1 by 3, values may change. Okay, here in this case even if you take one by one also, answer will not change. Okay, so that is beautiful here. Okay, so it is 3. Okay, total 3 are there. That means what? First equation 3 into VA self, no, plus 3. Okay, 3 VA. Next with respect to B node you have 1, so minus VB. Okay, then with respect to third node you have again 1 here, so minus VC. All the three are connected to this node, equal to how much current? So current entering the node is 9 amps, leaving the node is 3 amps here. So 9 minus 3, 6. So first equation is over. Similarly you can write that remaining 2. So next B node with respect to 1 we have to write 1 is there, so it is minus VA. Then 3 are there, so plus 3 VB. Then with respect to C you have 1. Okay, so it is minus VC, equal to current here is 3 amp. So 3 amp current is entering the node, only 3 amp, equal to 3. Similarly third equations, with respect to 1 you have 1 more, so minus VA. With respect to B you have 1, so that's why minus VB. Then self 1 1 1, 3 are there, plus 3 VC, equal to, now in this case 7 amp is current, so equal to 7. Simple. So you got the three equation, so just write down that equation and use the calculator, so you get the answer. So I have shown the answer in the next page, equation as well as the answers, just verify. Okay, so first equation as I told you, 3 VA minus 1 VB minus 1 VC equal to 6, 9 minus 3. Okay, at second one, minus VA plus 3 VB minus 3 VC equal to 3. Third one, minus VA minus VB plus 3 VC equal to 7. So use the calculator now. Okay, in equation mode, 3 unknowns. So this is A1 is 3, B1 is minus 1, C1 is minus 1, D1 is 6. Similarly, A2 is minus 1, B2 is 3, C2 is minus 1, D2 is 3. A3 is minus 1, B3 is minus 1, C3 is 3, D3 is 7. So with respect to calculator language I am talking here. So when you click enter, so you'll get the three values. So first value x equal to you are getting, which is VA, because in the equation I am written first VA, then VB, then VC, right? Accordingly it should be. Then second y equal to you are getting, then z equal to, okay, they are nothing but the VA, VB, VC, which is 5.5 volt, 4.75 volt and 5.75 volt. Okay, so just verify this answer, is it correct? So then your answers are correct. Okay, so hope, so with this you have understood now the difference between mesh and node. Okay, and how to write the node equations, and you have also understood the problems. So next we will see, using the node voltages, how we can find the branch currents also. Okay, so just one problem we will see in the next video. After that we'll see the super node analysis. Okay, with respect to dependent and all, I'm not considering that much. In the super node only I will club that. Okay, so you have understood in mesh analysis. Okay, fine. So with this I will end the session here. Thank you for listening. So work out, okay, write down this, okay, and see the video again and again if you have not understood. Okay, thank you.